electric potential and capacitance. An electric dipole is placed as shown in figure. Okay, the electric potential at a point capital P due to this dipole is, means this dipole is of length say 6 centimeter and the point of observation is at a distance 5 centimeter from the center of the dipole. So this point of observation is at a distance 2 centimeter from the positive charge and at a distance 8 centimeter from the negative charge. Okay, so the potential will be, see, due to the negative charge, the potential will be minus kq divided by 8 centimeter. We have to convert it into meter. So 8 into 10 raised minus 2. And due to positive charge, it will be kq divided by 2 into 10 raised minus 2. Okay, kq, this 10 raised to minus 2 is common to both the terms. Okay, so that can be taken outside. When it is taken to the numerator, it will be 10 raised to 2. And here we have minus 1 by 8 and 1 by 2. Okay, see, this is minus 1 by 8 and this 1 by 2 can be written as 4 by 8. Okay, so minus 1 by 8 and this 1 by 2 can be written as 4 by 8. So 1 by 8 is common. Okay, 1 by 8 that I have taken outside though. So inside the bracket there will be minus 1 here and plus 4 here. Okay, minus 1 plus 4. So it will be 3. So 3 divided by 8, okay, 3 by 8, then kq into 10 raised to volt. Okay, see, we have to find the answer in terms of, see, 10 raised to 2 volt. How many 100 volts are there? How many 10 square volts are there? Okay, so in units of 10 raised to 2 volt. So the potential will be 3 by 8 kq. 3 by 8, 3 by 8, this one. This is the correct option. Two charged spherical conductors of radii R1 and R2 are connected by a wire. Then the ratio of the surface charge densities on the spheres will be. See, when two spheres are connected by a conducting wire, they will attain a common potential. Okay, so the electric potential on the surfaces of both the spheres will be the same. See, the electric potential on the surface of a sphere is given by Q divided by 4 pi epsilon 0 R. Now the charge on the sphere can be expressed as surface charge density into surface area. Surface charge density means charge per unit area. Into area will give you the charge. So 4 pi r square into surface charge density sigma. Okay, so sigma r by epsilon 0. We have got two spheres and as they are connected by a conducting wire, the electric potential on the surfaces of both the spheres are the same. So as we move from one sphere to the other, this V remains same. Epsilon 0 is also same. So sigma r is constant. Okay, sigma r is constant in this case. Okay, or let us say sigma proportional to 1 by r. So sigma 1 by sigma 2 will be r2 by r1. So this r2 divided by r1. Okay, now let's see the next question. See, 27 drops of same size are charged at 220 volt each. They combine to form a bigger drop. Calculate the potential of the bigger drop. See, when n identical droplets each of radius small r combine to form a big drop, the total volume of the liquid will be conserved. See, this 4 by 3 pi r cube, that is the volume of liquid in each droplet. Such n droplets are there. So the total volume will be 4 by 3 pi r cube into n. Okay, combining these n droplets, a single drop will be produced and the volume of liquid in that single drop will be 4 by 3 pi r cube. Okay, so we will get capital R cube equals n into small r cube, or let us say capital R equal to n raised to 1 by 3 into small r. Okay, see, if small q is the charge on each droplet, then the total charge on n droplets will be nq. And the capacitance of the resulting drop, capacitance of an isolated sphere is 4 pi epsilon 0 r. Okay, here capital R is the radius of the sphere. So its capacitance will be 4 pi epsilon 0 capital R. Okay, that we can write 4 pi epsilon 0 n raised to 1 by 3 small r. Okay, this 4 pi epsilon 0 small r is the capacitance of each small droplet. Okay, so we have n divided by n raised to 1 by 3, that is n raised to 2 by 3. And small q is there, that is the charge on each droplet, and 4 pi epsilon 0 r is the capacitance of each droplet. So q by 4 pi epsilon 0 r is the potential of each droplet. So the electric potential of the resulting drop will be n raised to 2 by 3 times the potential of each droplet. See, each droplet was charged to a potential 220 volt, and 27 such droplets combine to form a big drop. This 27 can be expressed as 3 cube. Okay, so we have V equal to n raised to 2 by 3 V0, that n equal to 3 cube. So 3 cube whole raised to 2 by 3. Okay, that will be 3 square, or it is equal to 9. So the potential of the resulting drop will be 9 into 220, that is 1980 volt. Okay, so 1980 volt. Now let's see the next question. In a certain region of space with a volume 0.2 meter cube, the electric potential is found to be 5 volt throughout. The magnitude of electric field in this region is. See, electric field intensity is negative of the potential gradients, means change in potential per unit distance. See, here in a given volume, the potential is constant everywhere. So there is no change in potential, or potential does not change with the distance. So the intensity of electric field is 0. So intensity of electric field is 0. Okay. Now let us see the next question. We have a short electric dipole has a dipole moment of 16 into 10 raised to minus 9 coulomb meter. The electric potential due to the dipole at a point at a distance 0.6 meter from the center of the dipole situated on a line making an angle of 60 degree with the dipole axis is. See, this is the dipole, and here is the point of observation, and that point of observation is at a distance 0.6 meter. Okay, so r, this is equal to 0.6 meter, means it is 60 centimeter. See, the potential due to an electric dipole is given by this formula. See, Kp cos theta divided by r square, where P is the dipole moment. And here we have K equals 9 into 10 raised to 9. Dipole moment is given as 16 into 10 raised to minus 9 SI units. A theta is 60 degrees, so it is cos 60. And in the denominator we have 0.6 square. It will be 0.36 in the denominator. And this 16 cos 60 is 1 by 2. Okay, 1 by 2 into 16, that will be 8. That 8 I have written like 4 into 2. Okay, this 10 raised to minus 9 and 10 raised to plus 9 can be cancelled. So this 9 into 4, that is 36. 36 by 0.36, that is 100. 100 into 2, that will be 200 volt. Beautiful, right? 200 volt. Okay. See, a conducting sphere of radius r is given a charge capital Q. Electric potential and the electric field at the center of the sphere respectively are. See, at the center of the sphere, see, the intensity of electric field is 0. Intensity of electric field anywhere inside the sphere is 0 if it is a conducting sphere. Okay, so intensity of electric field at the center also 0. And the potential, see, electric potential at any interior points is the same as that on its surface. Okay, so in the intensity of electric field is 0 at the center, and the electric potential at the center is same as the potential on its surface, that is kq by r. So q divided by 4 pi epsilon 0 r. See, we have to find electric potential and electric field. That order is important. Okay, so electric potential means, so it must be in the order q by 4 pi epsilon 0 and 0. Q by 4 pi epsilon 0 r and 0. So this is the correct option. Okay. Now let's see the next question. Two metallic spheres of radii 1 centimeter and 3 centimeter are given charges minus 1 into 10 raised to minus 2 coulomb on smaller sphere and 5 into 10 raised to minus 2 coulomb on bigger sphere. Okay, if these are connected by a conducting wire, when two spheres are connected by a conducting wire, the charge will be redistributed. so that the potential on both the spheres are the same. Okay, or they will attain a common potential. Okay, now see, the total charge will remain conserved. First, on the first sphere we have -1, and on the second sphere we have 5. So the total charge will be -1 plus 5, that is 4 into 10 raised to -2 coulomb. When they are connected by a conducting wire, potential will become equal. V equal to kq by r. As we move from one sphere to the other, potential will not change, k will not change. Okay, so see, V by k equal to q by r, or q by r is constant, or q proportional to r. Okay, see, the charge on the two spheres q1 and q2 will be, q1 and q2 will be in the ratio r1 is to r2. Okay, because q directly proportional to r. So q1 by q2 will be r1 by r2. The radii are 1 centimeter and 3 centimeter. So q1 charge on the first sphere, finally after connecting them by a conducting wire, the final charge on the first sphere is q1 and the final charge on the second sphere is q2. Then q1 by q2 equal to r1 by r2 equal to 1 by 3. So total charge is 4 into 10 raised to -2 coulombs. That is to be divided in the ratio 1 is to 3. How do you divide? You have to divide the total charge into 1 plus 3, 4 equal parts. If the total charge is q, it is to be divided into 1 plus 3, 4 equal parts. Means q by 4, q by 4, q by 4, q by 4. Of which, see, q1 will be 1 part. Means q1 equal to q by 4, that is 1 part into 1. And q2 will be 3 parts. So q2 will be q by 4 into 3. Okay, the total charge is 4 into 10 raised -2. When it is divided into 4 equal parts, each part will be 4 by 4, means 1 into 10 raised -2. So the charge on the first sphere will be 1 into 10 raised -2. Charge on the second sphere will be 3 parts, so 3 into 10 raised -2. Okay, what we have to find out, see, the final charge on the bigger sphere, it will be 3 into 10 raised to -2 coulomb. Okay, now let's see the next question. 4 point charges minus capital Q minus small q, 2 small q and 2 capital Q are placed one at each corner of a square. The relation between capital Q and small q, for which the potential at the center of the square is 0. Okay, see, potential at the center of the square. See, this being a square, the distance from any corner to the center of the square will be the same, and let that distance be small r. Okay, so let us find the total potential at the center of the square. Potential being a scalar, total potential due to all the charges will be simply the algebraic sum of the potentials due to individual charges. Okay, first let us find the potential due to this. So it is minus k, k stands for 1 by 4 pi epsilon 0 minus kq by small r. Potential due to this is minus small k small q divided by r, and this is 2q, so k 2q by r, this is 2 capital Q. Okay, 2 k into 2 capital Q divided by r. Okay, k by r is common to all the factors, all the terms. Okay, that is taken outside. Okay, then minus capital Q and plus 2q. It will be plus capital Q. Minus small q and plus 2 small q. It will be plus q. Okay, this is the total potential at the center, and it is given that potential is 0. Then k by r is not 0. So q plus small q should be 0, or capital Q should be equal to minus q. So the first option. Now let's see the next question, the mean free path. Mean free path means the distance traveled by an electron between two successive collisions. Okay, mean free path of electrons in metal is 4 into 10 raised to -8 meter. The electric field which can give on an average 2 electron volt energy to an electron in the metal will be in units of volt per meter. Means as the electron moves through this much distance, it should acquire an energy equal to 2 electron volt. 1 electron volt is, see, 1 electron volt is 1.6 into 10 raised -19. That is the magnitude of charge on an electron, that much joule. Okay, So work done must be equal to 2 electron volt. Means 2 into electronic charge, that much joule. How do we find the work done? Force into distance. See, capital E is the intensity of electric fields. Then charge on an electron is small e, so this will be the force. Into distance, that is 4 into 10 raised minus 8. Force into distance will give you the work done. That is equal to 2 electron volt is equivalent to 1.6 or electronic charge, that much joule. Okay, so 2 into electronic charge, that much joule. We have to find capital E. So that will be the small e. See, this small e and small e can be cancelled here. Okay, this small e and small e can be cancelled. Okay, so capital E will be 2 divided by 4 into 10 raised minus 8 or 0.5 into 10 raised to 8 or let us say 5 into 10 raised to 7. Okay, this much volt meter raised to minus 1. The electric potential at a point in free space due to a charge capital Q is Q into 10 raised to 11. The electric field at that point is. See, electric potential due to a point charge is kq by r and electric field intensity is kq by r square. So electric field intensity is V by r. Okay, due to a point charge at a given point. So we have this V equal to 9 into 10 raised to 9 by into Q divided by r. And see, it is given as Q into 10 raised to 11. Okay, and R will be 9 into 10 raised to 9 divided by 10 raised to 11 or R equal to 9 into 10 raised to minus 2 meter. 9 into 10 raised to minus 2 meter. See, we want to find the intensity of electric fields. Okay, intensity of electric field, that is Q into 10. Intensity of electric field is potential divided by R. Okay, what is potential? Potential is Q into 10 raised to 11 divided by R. R is 9 into 10 raised to minus 2. Okay, 9 into 10 raised to minus 2. So see, I have multiplied this numerator and denominator by 10 raised to 9. Okay, so in the denominator I have this 9 into 10 raised to 9. 9 into 10 raised to 9 is 1 by 4 pi epsilon 0. So 1 by 9 into 10 raised to 9 is 4 pi epsilon 0. Okay, so 1 by 9 into 10 raised to 9 is 4 pi epsilon 0. Q also, then 10 raised to 20 divided by 10 raised to minus 2, that is 10 raised to 22. Okay, so 4 pi epsilon 0 capital Q into 10 raised to 22. 4 pi epsilon 0 capital Q into 10 raised to 22 volt per meter. Okay, now let's see the next question. From a point charge, there is a fixed point A. At A, there is an electric field of 500 volt per meter and a potential of 3000 volt. The distance between the point charge and the point A will be. See, this is the expression for potential due to a point charge and this is the expression for intensity of electric field due to a point charge. Okay, so V by capital E will give you the distance R. See, the potential is given as 3000 volts and intensity of electric field is given as 500 SI units. So 3000 by 500, that will be 6. Okay, so 6 meters. Now let's see the next question. We have a hollow metal sphere of radius 10 centimeter charged such that the potential on its surface is 80 volt. So at any interior point also the potential will be 80 volt only. The potential at the center of the sphere, of course, it is 80 volt. Okay, this is a wonderful, beautiful question. Charge plus Q and minus Q are placed at points A and B respectively, which are at a distance which are a distance 2L apart, where plus Q and minus Q are kept at a distance A and B respectively, which are plus Q and minus Q. So minus Q is here. Okay, here we have minus Q, right? A and B respectively, which are at a distance 2L apart. C is the midpoint between A and B. Okay, see, this is A, this is B, and C is the midpoints. Okay. Now the work done in moving a charge plus Q along the semicircle CRD. Okay. Now see, we have a minus Q here. See the distance from minus Q. See, distance from minus Q to the point C and to the point D are equal. See, potential being a scalar, it is independent of the direction. See, distance of minus Q from C and D are equal, or C and D are points at equal distances from minus Q. So the minus Q produces same electric potential at C, the initial position, as well as at D, the final position. Okay, so there is no change in potential due to the charge minus Q at the point C and D. We are moving a given charge between the point C and D. So we will have to find the potential difference between C and D. But this charge minus Q produces the same potential at C as well as at D. So as we move from C to D, there is no difference in electric potential due to the charge minus Q. So you need not bother about minus Q. Leave it. Now consider plus Q. See, this initial position C is at a distance L from plus Q, and final position D is at a distance C 3L from plus Q. Okay, so the potential difference is only due to the charge Q. Okay, so the potential due to Q at the final point, that is potential due to the charge Q at the final points. Okay, final point, that is potential at D minus potential at C. This will be K, that is 1 by 4 pi epsilon 0, and the charge is small q divided by 3L minus K small q divided by L. That is the point C. This is the potential at D and this is the potential at C. Okay. See, when a capital Q is at the point capital D, its potential energy will be this K small q capital Q divided by 3L. When that capital Q is at the point C, its potential energy will be K small q capital Q divided by L. So this is the final potential energy and this is the initial potential energy. That K I can replace by 1 by 4 pi epsilon 0. So this is the final potential energy and this is the initial potential energy. Okay, see, I have neglected the presence of minus Q because as we move plus Q from C to D, there is no change in potential due to minus Q because C and D, both the initial and final positions are at the same distance from minus Q. So you need to consider only the potential difference due to the charge plus Q. Okay, so this is the change in potential energy and it is equal to work done, that we will get minus Q divided by 6 pi epsilon 0 L minus Q small q, okay, Q small q divided by 6 pi epsilon 0 L. So this is the correct option. Okay, now children, let's try the next question. Okay, as per the diagram, a point charge plus Q is placed at the origin. Okay, fine. Work done in taking another charge. Okay. Here we have a charge plus Q. Okay, now see, this point A and this point B are equidistant from the origin where charge plus Q is kept. Okay, so the potentials at A and B are equal. Potentials at A and B are equal. Then the work done in moving any charge between these 2 points will be 0. Okay. Now let's try the next question. Okay, fine. This is also a beautiful question. See, we have a charge Q1 at A and another charge Q2 at B. Okay, a third charge Q3 is moved along the arc of a circle of radius 40 centimeter. Okay, from C to D. Q3 is moved from C to D. Okay, you have to listen carefully. See, this initial position C and final position D are at equal distance from A. So this charge Q1 produces the same potential at C as well as at D. So as we move a given charge from C to D, there is no change in potential due to the charge Q1. So the change in potential will be only due to the charge Q2. Okay, so we have to find the potential difference only due to Q2. Okay, see, this is 30 centimeter and this is 40 centimeter. So by Pythagoras theorem, see, this will be 50 centimeter, 50. The change in potential is, let me repeat, only due to the charge Q2, because we are moving a third particle Q3 from C to D. Okay, so the potential due to the charge Q2 at the final position, okay, final position, it will be Q2 divided by 4 pi epsilon 0. This distance is only, see, this is 40, so this will be 40 because it is the arc of a circle. Okay, arc of a circle. So this much is 30, so B to D will be 10. So the separation between B and D will be 10 centimeter. So when we place a charge Q3 here, the potential due to Q2 at the position D, potential due to Q2 at the position D, that is VD, this is equal to Q2 divided by 4 pi epsilon 0 into 0.1 into 0.1. That is the potential due to the charge Q2 at the point D. When Q3 is kept at that point, its potential energy will be this into Q3. Okay, that is the final potential energy of the system. See, final potential energy, say U2. Okay, when Q3 is at this point, it is at a distance 50 centimeter from Q2. So the potential energy will be, in the initial case, let me represent it as U1. Then Q2, Q3 divided by 4 pi epsilon 0, 50 centimeter, we can write 0.5. Okay, see, I have neglected the presence of Q1 because this Q1 produces the same potential at C as well as D. There is no change in potential due to Q1. So you need to consider only Q2. Okay, so this is the change in potential energy and it will give you the work done. Okay, and this is 10 Q2 Q3 and here it will be 2 Q2 Q3. So the difference will be 8 Q2 Q3 divided by 4 pi epsilon 0. Okay, 8 Q2 Q3 divided by 4 pi epsilon 0. Okay, so this K will be 8 Q1. Okay, 8, no, not 8 Q1, it will be 8 Q2, right? 8 Q2. The difference is only due to the presence of Q2. Okay, now let's see another question. A bullet of mass 2 gram is having a charge of 2 microcoulomb. Through what potential difference must it be accelerated starting from rest to acquire a speed of 10 meter per second? See, when it is accelerated through a voltage V, a charge acquires a kinetic energy QV. Okay, so QV equal to half mv square. Half mass is 2 gram. To convert it into kilogram, we have to multiply by 10 raised to minus 3. So 2 into 10 raised to minus 3. And velocity, final velocity is 10 meter per second. So V square is 10 square. Charge Q is 2 microcoulomb, so 2 into 10 raised to minus 6. Suppose it is accelerated through V volt, then Q into V. That V we have to find out, right? So V equals 0.5 into 10 raised to, how do we get that? See, this 2 and 2 can be cancelled. Then 10 raised to minus 3 and 10 raised to 2, that will be 10 raised to minus 1 and 10 raised to minus 6, that will be 10 raised to minus 5 on right. When it is taken to the left, it will be 10 raised to plus 5. Okay, 1 by 2 will be 0.5. So 0.5 into 10 raised to 5. Or we can write 50 into 10 raised to 3, or it will be 50 kilovolt. Okay, so 50 kilovolt, this one. Now let's see the next question. We have each corner of a cube of side L has a negative charge minus Q. The electrostatic potential energy of a charge Q at the center of the cube is. Q at the center of the cube is. Okay, now see, we have to find the distance from corner of the cube to its center. From corner of the cube to its center. Okay, so suppose a vector is drawn from one of the corners to the center. Okay, then suppose this is the x coordinate or x axis. We have see, each side is L, each edge is L. So from the, choose one of the corners as the origin. So L by 2 along the x-axis, then L by 2 along the y-axis, and L by 2 along the z-axis. Okay, so L by 2 I cap, okay, then L by 2 j cap, then L by 2 k cap. Then we will be at the center of the cube. So the vector drawn from one of the corners which is chosen as the origin to the center of the cube, it will be L by 2 I cap plus L by 2 j cap plus L by 2 k cap. So this is equal to L by 2 I cap plus L by 2 j cap plus L by 2 k cap. This is the vector drawn from one of the corners to the center of the cube if that corner is chosen as the origin. Then the distance from that corner to the center will be the magnitude of this vector. It will be under root L by 2 square plus L by 2 square plus L by 2 square, or under root 3 into L by 2 square, or we can write L by 2 into root 3, L by 2 into root 3. So the distance of the center from any of the 8 corners will be L by 2 root 3. And we have 8 identical charges each equal to minus q at each of the corners. So the electric potential at the center of the cube due to one of the charges will be 1 by 4 pi epsilon 0 minus q divided by r. R is L by 2 root 3. This is the potential due to each charge. And there are 8 such particles at equal distances from the center. So the total potential will be this into 8. This is the potential at the center where a charge q is kept. So the potential energy will be potential into charge. Okay, and here we will get this is minus 4q square divided by root 3 pi epsilon 0 L minus 4q square divided by root 3 pi epsilon 0 L, this one. Okay, then we have a simple network in which 3 capacitors each equal to 3 microfarad are connected. Okay, these two are in parallel. Effective capacitance will be 6 microfarad. It is connected in series with another 3 microfarad capacitor. So 3 and 6 are in series. So it will be 3 into 6 divided by 3 plus 6. That is equal to 2 microfarad. Okay, so this is the answer. Now let's see the next question. Okay, the effective capacitance of two capacitors are 3 and 16 when they are connected in series and parallel. Respectively, the capacitance of two capacitors will be. See, when two capacitors are connected in parallel, effective capacitance will be say if x plus y. Okay, so x plus y is 16. When they are connected in series, and if the individual capacitors are x and y, the effective capacitance when connected in series will be xy by x plus y, that is equal to 3. Okay, of which this x plus y, that is equal to 16. When this 16 is taken to the right, we will get xy equal to 48. So x and y, the individual capacitor values are such that their sum is 16 and their product is 48. So what you have to do now, you have to find out the factors of 48. Means which are the numbers whose product is 48. We can have 2 and 24. We can have 4 and 12. We can have 3 and 16. Okay, or we can have 8 and 6. All these numbers will multiplied to get a result that is 48. Their product should be 48, but their sum should be 16. Okay, so the factors must be 4 and 12. When they add this 4 and 12, we will get 16 and the product is 48. So the capacitors must be 12 microfarad and 4 microfarad. Okay children, let us see the next question. We have the distance between two plates of a parallel plate capacitor is doubled and the area of each plate is halved. If C is the initial capacitance, the final capacitance is equal to. See, this is the expression for the capacitance of a parallel plate air capacitor, epsilon 0 A by D. Now the area is made half, means instead of A we have to put A by 2, that I have done here. And the distance is doubled, means instead of D I have to put 2D. So this will be epsilon 0 A divided by 4D, or we can say C by 4. So the effective capacitance will be C by 4. Now see, we have a simple but beautiful question. See, a capacitor C equal to 900 picofarad is charged fully to 100 volt battery. Okay, it is then disconnected from the battery and connected to another uncharged capacitor of same capacitance 900 picofarad. The electrostatic energy stored by the system is. See, once the capacitor is charged and disconnected from the battery, whatever charge is stored in that capacitor, that will remain constant. Okay, initially, suppose the first capacitor holds a charge, say capital Q, then that capital Q will remain constant. Later, it is connected in parallel with another identical capacitor. So the effective capacitance will become 2C when two are connected in parallel. But the charge will remain as before, that is capital Q. So what happens now? Charge remains same, but the capacitance got doubled. Okay, then what happens to the energy? See, we have a wonderful formula for the energy stored in a capacitor, that is U equal to Q square by 2C. We have got two cases. In both the cases, Q is the same. So as we move from the first case to the second case, there is no change in Q. There is no change in 2. So Q square by 2 is constant as we move from the first case to the second case. This equal to, and in this particular case Q square by 2 is constant. This equal to and constant can be replaced by proportional to. Okay, usually we do in the reverse C order. So U proportional to 1 by C in this case. Earlier or initially the capacitance was C. Finally the capacitance is 2C because an identical capacitor is connected in parallel with the first capacitor. So the capacitance got doubled. See, energy proportional to 1 by C, inversely proportional to capacitance. When it is doubled, energy will become half. So in the final system, the energy stored will be only half of the initial energy. Okay, how do we find the initial energy? It is simply half CV square. That is half. Capacitance is 900 picofarad, means it is 10 raised to minus 12, and voltage is 100. Okay, 100 square means it is 10 raised to 4, and here we have to see 900 means 9 into 100. That 100 and 10 raised to 4, that is 10 raised to 6, and 10 raised to minus 12, that is 10 raised to minus 6. Okay, 9 by 2 will be 4.5. This much joule is the initial energy, but the final energy only half of that. See, half of 4.5 will be 2.25. So 2.25 into 10 raised to minus 6 joule. Okay. Now let's see. A parallel plate capacitor has a uniform electric field capital E in the space between the plates. If the distance between the plates is d and the area of each plate is capital E, the energy stored in the capacitor. Okay. See, this half epsilon 0 E square, that is the energy density, or it is the energy per unit volume. Energy per unit volume. Half epsilon 0 E square. Beautiful formula. Okay, energy per unit volume. Suppose we have got two plates, each of area capital A, separated by a distance d. Then the volume enclosed by these plates in between them, that will be A into D. And unit volume holds an energy half epsilon 0 E square. Then the total energy in a volume AD will be half epsilon 0 E square AD. That is the energy stored. Okay, so energy density, yeah, we have the same procedure here. Now children, we have another beautiful, wonderful question. Two identical capacitors C1 and C2 of equal capacitance are connected as shown in figure, and terminals A and B of the key K are connected to charge capacitor C1 using battery of EMF V volt. Okay. Now disconnecting A and B, the terminals B and C are connected. Due to this, what will be the percentage loss of energy? See, exactly similar question we have done just before. Okay, see, the case here is initially this C1 is connected to the cell. So this C1 will get charged to V volt. The energy stored in it will be half C1 V square. Okay, now see, it is disconnected from the cell. Okay, so some charge will be stored in the capacitor, it will remain constant. Now that capacitor is connected in parallel with another identical capacitor. Charge remains same, but the capacitance got doubled. Okay, see, as I have told you earlier, See, we have the wonderful formula for the energy stored in a capacitor, Q square by 2C. Here Q square by 2 is constant because charge does not change, 2 also constant. So capacitance inversely, this energy U inversely proportional to capacitance. Capacitance gets doubled, so energy will become half. Okay, energy becomes half, means half of its energy initially stored will be lost. So the percentage loss will be 50%. This is the simplest way of doing it. Okay. Next, I think, this a capacitor of 2 microfarad is charged as shown in the diagram. When the switch S is turned to position 2, the percentage of its energy stored dissipated is, okay. See, once it is charged and disconnected from the battery, the charge on the capacitor will remain constant. Okay, charge on the capacitor remains constant. So the energy stored in the capacitor is Q square by 2C. Okay, and energy proportional to 1 by C because charge does not change. Initially the capacitance was 2 microfarad, then it is connected in parallel with another 8 microfarad capacitor, means the capacitance will become 2 plus 8, 10. Initially 2, finally 10. Means the capacitance will become 5 times. And the energy is inversely proportional to capacitance. So when the capacitance becomes 5 times, energy will become 1/5. 1/5. So the final energy will be only 1/5 of its initial energy. Means 4/5 of its initial energy is lost. The energy lost, fractional energy lost is 4 by 5. So the percentage energy lost is 4 by 5 into 100. That will be 80%. Okay, 4 by 5 into 100, 80%. Here we have U dash divided by U, that is equal to C divided by C dash because inversely proportional to capacitance. C is 2 microfarad, C dash is 10 microfarad because 2 and 8 are in parallel. Finally, that is equal to 1 by 5. So U dash divided by U into 100, that is 20%. Final energy is only 20%. So the energy loss will be 80%. Okay. Now this is also a very good question. A parallel plate air capacitor of capacitance C is connected to a cell of EMF V and then disconnected from it. A dielectric slab of dielectric constant K, which can just fill the air gap of the capacitor, is now inserted in it. Which of the following is which of the following is incorrect? Incorrect. Wrong statement we have to find out. Okay, no problem. See, the main thing is it is then disconnected from it. Disconnected from it. What does it mean? The charge stored in the capacitor will remain constant. That is the point number 1 when it is disconnected. Now, when a dielectric slab is inserted between the plates, or when the plates or the space between the plates is filled with the dielectric, capacitance will become K times. With the air, the capacitance was C0. When the space between the plates is filled with the medium of dielectric constant K, the capacitance will be KC0. That is point number 2. Capacitance will become K times, charge will remain constant. 2 points. Okay. Now first statement, the energy stored in the capacitor decrease K times. Okay. Let's check. See, energy we have Q square by 2C. See, this Q does not change. So this Q square by 2. See, Q does not change. So this Q square by 2, this is constant. So energy proportional to 1 by C. When capacitance becomes K times, energy will decrease K times. Okay, or energy will decrease K times. So first statement is true, correct. We have to identify the wrong statement. So this is not wrong. Okay, now second, the change in energy stored. Energy stored will become 1 by K times. Okay, change is always final minus initial. Okay, what is final energy? Initial energy is is U0. Final energy U will be U0 by K. So the change in physics is always final minus initial. So initial energy U0 by K, initial energy is U0, final energy is U0 by K. So final minus initial. U0 we can take outside. So 1 by K minus 1. U0 is initial energy and it is half CV square. So half CV square into 1 by K minus 1, that is the change in energy. It is also true. Okay. The charge on the capacitor is not conserved. No. Charge on the capacitor is conserved. So this is the wrong statement and that is our answer. Okay. Now let's check the final statement. The potential difference between the plates will decrease K times. See, we have potential V equal to Q by C. Q does not change, but capacitance will become, if Q is constant, then let us say potential proportional to 1 by C. When capacitance becomes K times, potential will decrease by a factor K or becomes decrease K times. Okay, that's fine. So statement C is the wrong statement. We have to identify the wrong statement. Okay, children, let's see the next question. A parallel plate air capacitor has capacitance C. Distance of separation between the plates is D and the potential difference is V. Okay, the force of attraction between the plates of the parallel plate air capacitor is CV square by 2D. CV square by 2D. This is the answer. We have a plate. Okay. Now the intensity of electric field due to this charged metal plate in front of it, that is sigma by 2 epsilon 0. There is no distance in that formula. Means the intensity of electric field in front of this plate is independent of the distance. See, everywhere in front of this plate, the intensity of electric field is the same. Okay. Now suppose I have kept an identical plate very close to it, means the separation between them is infinitesimally small, negligible. The force of attraction, let it be F. Okay, as we separate these two plates, the force will remain constant, independent of the distance between them. So as we separate these two plates, we will have to do work against a constant force, capital F. That is the force of attraction between the plates. And suppose we have separated the plates through a distance D, then the work done in doing so will be force into distance, F into D. That will be stored in the capacitor as its energy half CV square. So we have force into distance, that is the work done, that is equal to half CV square. Then the force of attraction between the plates of the capacitor will be CV square divided by 2D. 3 capacitors, each of capacitance C and of breakdown voltage capital V, joined in series. Means V is the maximum voltage that can be applied across each capacitor. Okay, the voltage across any capacitor should not exceed V. Okay, the capacitance and breakdown voltage of the combination will be, when they are connected in series, effective capacitance will be C by 3. But each of these capacitors can withstand a voltage V, so the combination can withstand a voltage 3V. So C by 3 and 3V, this one. Now let's see the next question. We have two condensers, that is an old name used for this capacitors. You should not use that. Two capacitors, not condensers. Capacity. It should be two capacitors, each of capacitance C and two capacitors of capacitance C and C by 2 are connected to V volt battery as shown. Work done in charging fully both the capacitors will be. Okay. Now we have two capacitors C and C by 2 connected in parallel. So the effective capacitance will be C plus C by 2. That is 3C by 2. Voltage applied is what? V. So the energy stored will be half effective capacitance into V square. That is half 3 by 2C into V square. This is 3 by 4 CV square. Okay. Now let's see the next question. Right. A parallel plate air capacitor is charged to a potential difference V volt. After disconnecting the charging battery, means the charge will remain constant. The distance between the plates of the capacitor is increased using insulating handle. As we are using insulating handle, the charge will again remain constant. And when we increase the separation, capacitance will get reduced. Okay. As a result, the potential difference between the plates will increase. Because we have moved apart now. See, Q is the same. Capacitance is epsilon 0 A by D. When D is increased, capacitance will decrease. See, here we have V equal to Q by C. See, V equal to Q by C. Q is constant and C is decreased, reduced. Okay, so voltage will increase. So this must be the correct answer. Okay, now let us see the next question. A network of 4 capacitors equal to C1C, C2 2C and C3 3C and C4 4C are connected to a battery as shown in figure. The ratio of the charges on C2 and C4 means we have to find charge on C2, let it be Q2, divided by charge on C4, let it be Q4. So Q2 by Q4, that ratio we have to find out. See, this C4 is connected directly across the voltage. So the voltage across C4 will be V itself. This voltage V will appear across C4. Okay. And its capacitance is 4C. Voltage is V. So the charge on the capacitor C4, that is equal to Q4 and it is 4CV. Okay. See, Q4. This is equal to 4C into V. Okay, 4C into V. That is Q4. Now we have to get Q2. See, this is C, this is 2C, this is 3C. These three are connected in series across this voltage V. As these three capacitors are connected in series, the charge on all the three capacitors will be the same. Okay. See, when a number of capacitors are connected in series, charge will be same. When they are connected in parallel, voltage will be same. When a number of resistors are connected in series, current will be same. When a number of resistors are connected in parallel, voltage will be same. Here 1, 2, 3, C1, C2, C3 are connected in series, charge on all the capacitors will be the same. The voltage across each capacitor is given by V equal to Q by C, in which Q is constant. So voltage is proportional to 1 by C. So V1 is to V2 is to V3 will be in the ratio 1 by C1 is to 1 by C2 is to 1 by C3. So V1 is to V2 V3. This is equivalent to 1 by 1 is to 1 by 2 is to 1 by 3. Because C1, C2, C3 are 1, 2, 3 respectively. Okay. So V1 is to V2 is to V3 is 1 by C1 is to 1 by C2 is to 1 by C3. We have the ratio like this. Okay, to convert it into a simple ratio, we have to multiply throughout by the LCM. That is, here it is 6. So multiply throughout by 6, we will get 6 is to 3 is to 2. So the total voltage V is to be divided. Total voltage V is to be divided in the ratio 6 is to 3 is to 2. How do you divide the voltage V in the ratio 6 is to 3 is to 2? You have to divide V into 6 plus 3, that is 9, plus 2, that is 11. So V is to be divided into 11 equal parts. Each part will be V by 11. V by 11, V by 11, V by 11, like that 11 parts. In which the voltage across the first capacitor will be 6 parts. Means 6 into V by 11. Voltage across second capacitor will be 3 parts. 3 into V by 11. Voltage across third capacitor will be 2 parts. How many parts are there? 11 parts. So the voltage across the third capacitor will be 2 into V by 11. We need the voltage across the second capacitor. It is 3 parts. So the voltage V2 across the second capacitor will be 3V by 11. Okay, so Q2, that is equal to C2V2. C2 is 2C, voltage across it is 3V by 11. Okay, and C4 is 4C, the voltage across it is complete V. Okay, so we will get C will get cancelled, V will get cancelled, 2 and 4 will get cancelled, so it is 3 over 22. 3 over 22 means this will be the answer. Okay, the capacitor C1 is charged to a potential difference V. The charging battery is then removed, means its charge on the first capacitor C1 will remain constant. The capacitor is connected to an uncharged capacitor C2. The potential difference across the combination is. See, the charge on the first capacitor is C1V, that will remain constant. Finally, the capacitance is C1 plus C2. So the final voltage will be charged by capacitance. So C1V divided by C1 plus C2. C1V divided by C1 plus C2. C1V divided by C1 plus C2. This is the final voltage across the two capacitors. Okay, in a parallel plate capacitor, the distance between the plates is d and the potential difference across the plates is V. The energy stored per unit volume. What is the formula? That is half epsilon 0 E square. And intensity of electric field we can write V over D. Okay, so it will be half epsilon 0 V square by D square. Half epsilon 0 V square by D square. Beautiful formula, right? Now see, we have the capacitance of a parallel plate capacitor 10 microfarad when distance between the plates is 8 centimeter. If the distance between the plates is reduced to 4 centimeter. See, capacitance is epsilon 0 A by D. When the distance is reduced to half, capacitance will become twice, because capacitance inversely proportional to distance. Originally it was 10 microfarad, so now it will be 20 microfarad. Okay, capacitor is charged to store energy U. The charging battery is disconnected, means the charge will remain constant. An identical capacitor, how many times we have done this? An identical capacitor is now connected to the first capacitor in parallel. So capacitance will become twice, so energy will become half. The energy in each of the see, total energy is U by 2. So the energy in each capacitor will be U by 4. Okay, so the answer is U by 4, not U by 2. You have to be careful. Please read the question carefully before you answer it. Okay, the energy in each of the capacitor is U by 4. Okay, now let's see a parallel plate capacitor with oil between the plates has capacitance C. If the oil is removed, then the capacitance will become half C by 2, because epsilon 0 Ka by D is C. So epsilon 0 A by D, that is the air capacitance, it will be C by K, and K is given as 2. So it will be C by 2, right? Now, we have what is the effective capacitance between points X and Y. See, here X is same as A actually, and Y is same as D, right? Okay, so A is same as X, X, and D is same as Y. Okay, so capacitance between X and Y means capacitance between A and D we have to find out. Okay, see, this is a Wheatstone's bridge. How do we check whether it is balanced or not? See, if the ratio of the adjacent arms are equal, then the bridge is balanced. Then this capacitor C5 can be eliminated or removed from the network if the bridge is balanced. And the condition for a balanced bridge is ratio of the adjacent arms should be equal. How do we find the adjacent arms? Adjacent arms means C1 and C2 adjacent arms, or C1 and C3 adjacent arms. Means adjacent means we have to take in this way or this way. Any way you can take. See, you can take this way. If you don't like that, you can take this way. If C1 by C2 equal to C3 by C4, bridge is balanced, C5 can be eliminated. Or if C1 by C3 equals C2 by C4, then also bridge is balanced. C5 can be eliminated. But children, you see, you can check the condition for balanced Wheatstone's bridge by a better way. That is, bridge is said to be balanced if the product of the opposite arms are equal. Ratio means it is division. Product means it is multiplication. Even though we are familiar with the multiplication and division, multiplication is more comfortable. Even though you are familiar with the addition and subtraction, addition is more comfortable. So it's always better to check the condition by multiplying the opposite terms. If C1, C4 equal to C3, C2, the bridge is balanced. Here we have, see, this one and this one, right? 6 into 6, that is 36. Okay, then this is 6 and this is 6. Okay, all the four capacitors, all the four arms are of equals. So the bridge is balanced. The effective capacitance will be 6 itself. Okay, so it will be 6 microfarad, because this can be removed. See, this can be removed, this can be removed. Then this 6 and this 6 are in series. It will be 3. Again, this 6 and 6 are in series. Another 3. This 3 is in parallel with this 3. So the effective capacitance will be 6 microfarads. Okay, right. So the answer is 6 microfarads. Okay. Now see, let's do the next question. If the potential difference of a capacitor 6 microfarad is increased from 10 to 20, the increase in energy will be energy stored in a capacitor is half CV square. When the voltage is increased from 10 to 20, it will be half C 20 square minus 10 square, and capacitance is 6 microfarad. Microfarad means 10 raised to minus 6, half into 6 into 10 raised to minus 6, and 20 square is, that is 400, 10 square is, that is 100, so 400 minus 100 will be 300. Okay, now 6 into 3, that is 18 by 2, that is 9. Here we have 100 and 10 raised to minus 6, that is 10 raised to minus 4. So 9 into 10 raised to minus 4 joule. Here we have. Okay, 4 microfarad conductor. No, capacitor. Okay, charge to 400 volts and then its plates are joined through a resistance of 1 kilo ohm. The heat produced in the resistance is equal to energy stored in the capacitor. It is not conductor, it may be condenser or it can be capacitor. Okay, anyway, it is not a conductor. So it is half CV square, that is the energy stored in the capacitor. It will be dissipated in the form of heat. Here we have capacitance 4 microfarad means 4 into 10 raised to minus 6, and the voltage is 400 volt. So 400 square means 16 into 10 raised to 4. 16 into 4, that will be 64 by 2, that will be 32 into 10 raised to minus 2. 32 into 10 raised to minus 2, or it will be 0.32 joule. 0.32 joule. Okay, now see, that is the end of this chapter. We have discussed all questions from this chapter so far asked for NEET or earlier AIPMT. So you need to expect only this level of questions, this type of questions. So if you understood all these problems, then you can be confident that you will be able to solve any question that will come for NEET, next NEET also. So wish you all the best. Thank you for watching this video.